videos of this, and they'll be on Facebook and YouTube later on this evening, honest gut. So I'm looking forward to seeing that come out. Any ideas, Pete's around, when we're going to get those up? Look for them in the morning, is it? No, okay. Oh, in the morning, Pete? Yep, I've just seen the thumbs up sign, so that's it. So this evening will be preserved for posterity on the internet, which will be great. Well, moving on then, we now have Dr. Ben Evans, who's going to talk to us about Bloodhound, the 1,000-mile-an-hour engineering adventure. Ben.
Wel, noswaith dda I bawb. Diolch yn fawr am ddod. Can you all hear me? Can you hear me too loud? Yes. Okay. Thank you very much for coming. It's great to be at events like this because I spend a lot of my time locked away with some very intelligent engineers, often locked away in my own office. But actually, Bloodhound is all about sharing engineering and sharing science. So as I mentioned earlier, actually this isn't just about designing the world's fastest car, although that is primarily what I'm going to talk about tonight. It's also about sharing this project as widely as we possibly can. So what is the Bloodhound Project? Is there anybody here who'd never heard of the Bloodhound Project until tonight? There's a couple of you. Okay, so the gospel is spreading. What I'm going to do, just to kind of set the scene for all of this, and to try and explain why this is much more than just designing the world's fastest car. I'm going to show you a short movie which explains really the first question I asked back in 2007 when I was invited to be a part of this project. The question of, well, why on earth are we doing this? The UK was entering into an economic recession, and I was being told that what we really needed to do in the UK was design a 1,000-mile-per-hour car. And this is the movie that explains why we're doing it.
This is the most extraordinary project I have ever been involved in. What we're doing is creating the most advanced land-speed record car that's ever been built.
Bloodhound SSC has a very unusual objective for a land-speed record project. It's not to set a speed or even a new record. It's to get everybody from 6 to 96 years old, interested and excited by mathematics, engineering, science, technology.
The objective here is to share the project and all its technology as widely as we possibly can. But the key thing to all this is education. Whether it could be bridges, whether it could be fashion, it could be fast cars. People love engineering.
I am a Royal Air Force fighter pilot, but first and foremost, I'm a mathematician. And that is the way I not only think about numbers, incredible numbers involved in flying fast jets from day to day, but also the truly astonishing numbers that Bloodhound SSC is throwing up.
Just to give you an idea, the bodywork at these speeds has got to take loads of the order of 12 tons per square metre. It's got to be as tough as a submarine. Nobody's ever done anything like this before.
When we are accelerating this car, it's going to be peaking at 3G, 60 miles an hour per second. At peak speed, it will be covering the length of 4 football fields per second. The wheel rims will be experiencing 50,000 radial G at the rim. Those sorts of numbers are truly astonishing, and if you don't understand them, truly frightening. And as the driver, actually that's not a good thing. I'm in the lucky position, as the world's fastest mathematician, of being able to understand, be comfortable with those numbers, understand the engineering solutions.
We have to remember that this is an adventure. It's an engineering adventure. We don't know what the final outcome is going to be. And even if we don't get to 1,000 miles per hour, it won't necessarily be a failure if what we have done is inspire people.
There's going to be a huge industrial revolution. And to cope with this, we've got to have the scientists. We've got to have people studying mathematics, science, engineering. Because basically, unless we do this, Britain simply isn't going to be able to play.
Okay, so we made that movie 6 years ago. so I was looking a little bit younger back in those days. And I'm really proud to say that we are starting to achieve this. There are, at the moment, over 5,000 schools signed up to our education programme. And if you're connected to a school in the local area and your school isn't involved in Bloodhound, come and see me at the end and I'll explain how you can get involved. But what I'm going to talk about this evening is this engineering objective here. We're going to try and take the land speed record within the next 1 or 2 years to this incredible, ambitious target of 1,000 miles per hour. That means the top speed that the car will travel at throughout the measured mile is 1,050 miles per hour. So we've, over the last 5 years or so, we're trying to design a car that we believe is safe and is going to achieve this. Professor Hassan touched on some of this, the history of the land speed record earlier, so I won't dwell on this, other than to point out that what we're trying to achieve with Bloodhound, without any shadow of a doubt, is incredibly ambitious. In fact, in some of the early design meetings I sat in on, when there were just a handful of us sat around a table in Ron Ayres' living room, one of my concerns about this project was that if we're setting ourselves and we're going to go to the press with this target speed of 1,000 miles per hour and advertise this as the 1,000 mile per hour car, well, what if we do something fantastic and take the land speed record to 900, 950 miles an hour, but don't quite get to 1,000 miles per hour? Does that mean people perceive it as being a failure? But Richard Noble, being the kind of person he is, and knowing what he needed to say to get sponsors on board, said, no, this is going to be a 1,000 mile per hour car. So it is incredibly ambitious. We are diving into an aerodynamic speed regime that really we've never been to before. Thrust SSC was the first car to go supersonic. It did that for fractions of a second, or just for a few seconds. It nudged across the sound barrier and quickly came back. What we're going to be doing with this vehicle within the next couple of years is taking a land-based vehicle right into that supersonic speed regime and staying there for a sustained period of time. So what's so difficult about designing a supersonic car? Well, I guess in many ways, some of the things that are difficult about designing Bloodhound are the same things that were difficult about designing Thrust SSC. We've got these shock waves to deal with that Professor Sam was talking about earlier. We've got a significantly bigger drag that we're going to have to counteract with Bloodhound. The drag on a vehicle like this varies with the square of speed. So going from 763 to 1,000 miles per hour means that there's a significantly increased drag that this car will experience. But essentially, at the root of the work that I've been doing, one of the big challenges is understanding where on this vehicle the shock waves are going to form, what they're going to do to the desert that the car will be rolling over, and what they're going to do to the car itself. I've got a little movie here, just to give you an idea of what this might feel like if you were alongside the track when Bloodhound is running, and it passes you at supersonic speed, the kind of sound you would hear as a shockwave passes you by. This is a fighter jet passing a ship faster than the speed of sound, just to give you a feel of what this might be like. So as Obey was explaining earlier, what that is that shock cone that's fanning out from the aircraft and will be fanning out from Bloodhound. And you heard it in the movie that Obey played right at the very end as well. As the car passed, there was this big sonic boom. So the question, once you kind of understand the complexity of the aerodynamics, is, well, how do you overcome the drag, first of all? How do you keep it on the ground? And how do you make sure the whole system of forces is stable? How do you design an aerodynamically stable car that's not just stable when it's travelling at supersonic speeds, but it's also stable when it's travelling at subsonic speeds? Because even if something went wrong at the subsonic speed of 300, 350 miles an hour, that would be a pretty nasty incident. Can you keep it stable through the transonic regime, where you've got lots of shock waves moving around on the car? This is the crux of the question we've been trying to answer. And fortunately tonight, I usually at this point try and explain what CFD, computational fluid dynamics, is, what meshes are and what the finite element method is. But Professor Sam has done that for me tonight. So we use computers. Okay, so we do what CFD is, computational fluid dynamics is. It's essentially virtual wind tunnel modelling. So traditionally we might have tried to understand the aerodynamics of a vehicle like this in a wind tunnel. Instead, we use this rather large computer, which is just down the road within the university, and that's me in my office connected to it. To give you an idea of the scale of this machine, that's me and an ex-student of mine standing next to it. And essentially what we've got in here, which is doing the number crunching that Obey was talking about earlier, is essentially a lot of PCs wired together in a very efficient and fast connection system. So this is what we call a PC cluster, and this is our PC cluster that we've used for lots of the simulations that I'm going to talk about tonight. Now, at the end of that whole process that Obey was talking about, this CFD, this simulation process, we get the thing that we all really want, which is pretty pictures. Now, what I'm going to show you here is the results of one of the simulations, or a suite of simulations that we ran many years ago, back in the early stages of the design of Bloodhound. What I'm going to be showing here are pressure patterns. Ultimately, it's pressure that drives the forces on a vehicle like this. If you can understand what the pressure distribution is doing over this vehicle, then you can sum up that pressure distribution or integrate that pressure distribution over the surface of the vehicle and work out what the overall forces are. Now, in these plots here, the purple colours are very high pressure, so this is where you've got a lot of force pushing down on the surface. And then you go through purples and blues and turquoises, greens, oranges, and then the reds are very low pressure. They're actually suctions. This is where the air is actually trying to suck on the surface. So if it's a red colour on the bottom of the car, which is what you're looking at on the left-hand side, that's sucking the car down onto the ground. So you can see at the back of the car here at subsonic speeds, where Mach 0.8 means you're travelling at 80% of the speed of sound. You've got a lot of suction at the back end of the car, pulling the back end onto the ground. Conversely, where you've got purples underneath the car, this is high pressure trying to push the car up or lift it off the surface. So in very simplistic terms, what we've always tried to do as we've evolved the design of this car is look at pressure plots like this and try and remove all the purples and blues from the underneath of the car and get them onto the top of the car, because that means that the car is being pushed onto the ground. But what we're also interested in is what the car is going to do to the surface it's running over. Because, of course, if the front of the car destroys the surface that it's running over, then there's no surface left for the rear of the car to run over. So what we've tried to do is minimise the strength of the shock waves that interact with the ground, which you'll see in a moment when I run the simulation. So what I've got here is a plot of the desert surface the car is running over. The scale is slightly different on these two plots. So these two little dots here correlate to the front wheels of the car, and these two dots here correspond with the rear wheels. So we're zoomed out on the right-hand side. Now, if I run this simulation, the car's going to accelerate through the sound barrier. So you can see the Mach number is approaching Mach 1. And as it approaches Mach 1, you can see straight away an awful lot more purple underneath the car. And you can see these three distinct features here, which are the three shock waves, the three strong shock systems that will be featuring on the car. Does anybody, kind of knowing what you know now from tonight about why shock waves form, does anybody want to have a go at guessing? Well, let's go with the first. The first shock is the traditional bow shock. So that the car is passing through the air has to suddenly pressurise to squeeze around the car and forms a shock wave. There's a second shock wave here. Does anybody want to have a guess at what that shock wave is associated with? It's not the wheels. It's not the first reflected shock either. It is, yes. I think somebody shouted out both contributions. So it's to do with the cockpit and the air intake. You can imagine you're a parcel of air that's been sitting ahead of the car as it's come towards it. It's suddenly had to compress as the nose reaches it, to squeeze around the nose of the car. And then, of course, it gets to this point where there's a now sudden expansion in the geometry of the car because you've got the cockpit and the intake duct. It suddenly has to squeeze again, and that squeezing, that pressurization of the air is a shock wave. So that's what this second shock wave is here. And there's a third shock wave here. Does anybody want to have a go at guessing what that is generated by, or why that is generated? It's not to do with the exhaust. Yes, somebody shouted that. It's the rear wheels. Because, of course, you can imagine, again, you're a parcel of air. It's passed through the first shock wave associated with the bow of the nose of the car. It's passed through a second shock wave associated with the cockpit and the intake duct. It thinks it's home and dry now. It thinks all it's got to do is just slide down the side of the car and then expand again when it reaches the back of the car. And, of course, there are these two great big 1 metre diameter rear wheels out in the airflow that it has to suddenly compress to squeeze around again. And actually, in terms of the aerodynamic design, the aerodynamic stability of the car, it's the shock wave at the back that's caused us the biggest problems. We probably spent a good 6 months just playing with the geometry of the rear wheels, the fairings that shroud those rear wheels to try and minimise the strength of the shock wave at the back. If you remember what the pressure pattern was like at subsonic speeds, there's an awful lot of red at the back here. So at subsonic speeds at the back of the car is being sucked down onto the ground. Now at supersonic speeds, there's an awful lot of purple, which means it's being pushed up onto the ground. And this configuration, which was about configuration 4 or 5 in the design evolution of the car, this car would have lifted up off the ground at about Mach 0.9, we showed. So we had a lot of work to do at this stage. Now, I'm going to test you because Obey showed a slide very similar to this for thrust earlier on. One of the things I love about my job is that I get to go out and talk to lots of people about what I do. And I spend a lot of time going into schools, right through from primary age all the way through then to secondary and further education colleges, and give lectures at times like this. And I always do this exercise because it's really interesting to see what I get shouted at me. Now, the answers to the question I'm going to ask you were given in Professor Hassan's slide. Does anybody want to have a shout out, particularly if you're a younger person and you're studying this kind of thing in school, does anybody want to have a shout out at some of the forces that will be acting on Bloodhound? Imagine it's travelling on the desert at 1,000 miles an hour, some of the forces that will be acting. Yeah. Lift, absolutely. Okay, so just like an aircraft, if there's air travelling over a body like this, it can generate lift. Of course, what we're hoping is that lift will have a negative value, it will be a downforce. But yeah, it's a vertical force due to the air. Anything else? Drag. Okay, so we talked about it already. There's a resistive force that the air can impart on a body like this. So we've got lift and drag. Gravity. Okay, so the car's got mass, just like we have mass. So the force of gravity is acting on that mass, pulling it down towards the centre of the Earth. So we've got lift, drag, gravity. Thrust, okay, so something's got to make this car go, something's got to overcome this drag force to cause it to accelerate. We've got two sources of thrust on the car. We've got a jet engine and a rocket engine, which I'll talk about and do a little demo on in just a moment. So we've got lift, drag, thrust, gravity. And there's one more. Power? There's power. The power gives the car the thrust. So the power is what generates the thrust on the car. It's important. Technically, it's not a force, though. Weight we've had. Sorry? Oh, well, that's to do with kind of the motion of the car. But again, it's technically not a force. There's friction, but I'll wrap that all up in the drag term. And this is a force, and this is always, wherever I go, no matter whether it's a primary school or a university lecture, this is the last force that people remember. And it's ironic because it's one that's acting on all of us right now. You guys, it's primarily acting on your bums. Me, it's primarily acting on my feet.
Gravity.
It's not gravity. Yeah. Absolutely, okay? There's the reaction force. The reason we're not all plummeting down towards the centre of the Earth right now, even though there's the force of gravity trying to get us there, is that there's a floor and a seat that's pushing back up on us at what we call a reaction force. Okay? If you're doing GCSE physics, you should have that nailed. So here they all are. And these are all the forces acting on the car. If we can understand how all of those forces vary with the speed of the car, then we can predict in advance, using force equals mass times acceleration, Newton's second law, we can work out how fast it's going to accelerate and the motion of the car. Now, the lift force and the drag forces are the two forces that's been our responsibility at Swansea to predict. The other forces, in many ways, are quite easy to predict because the jet engine manufacturer tells you how much thrust its engine can produce. The rocket tests we've been doing tell us how much thrust the rocket engine produces. We know what the mass of the car is going to be as it burns fuel. We know what its starting mass is. We know what rate it burns fuel. So all the other forces are actually quite easy to predict. The difficult ones to predict are the ones that we've been predicting in Swansea, the lift and the drag. So, that kind of exercise naturally leads us into this next question, which is, well, obviously to get a car travelling at these incredible speeds, you're going to need a lot of this force called thrust. So we've got not one engine delivering thrust, we've got two engines delivering the thrust on the car. And the first one, we've stolen from this aircraft here. This is the Eurofighter Typhoon. We haven't actually stolen it. We did ask the MOD if we could borrow a couple. Officially, we're supposed to be giving them back at the end, but I can't imagine that's ever going to happen. So the MOD have lent us 3 of these EJ200 jet engines. We're only going to be using one at a time, but we've got 3 in case we damage any of them. So this is the engine that the Eurofighter has 2 of these, and when it's delivering its maximum thrust with the afterburners firing, it generates 9 tons of thrust, or 90 kilonewtons of thrust. It looks something like this. This is the engine that's going down into the belly of the car. And I think what I've got here is a movie that demonstrates how this works. Now, most of us are, to some extent, familiar with jet engines, because lots of us, I would imagine, have flown on aircraft powered by jet engines. Quite often they're slung under the wings of the aircraft. And the way they work is you have a compressor or a fan on the front, which sucks air in and compresses it, increases its pressure and temperature. That air, oh, sorry, I didn't mean to do that. That air then passes into combustion chambers, where the fuel is added and ignited. Because of that reaction, the temperature and the pressure goes up even higher. And then the air expands through a turbine at the back. And the spinning of this turbine connected to this shaft is what's driving the fan at the front. And this thing just keeps getting faster and faster and faster until it reaches the maximum speed of the engine. And then you've got all this high pressure, high temperature gas, which expands and accelerates through this nozzle at the back. And because we're going from a large area to a small area, it's accelerating. And again, it's Newton's third law that is the source of delivering the thrust. If you're in school, and that's confusing, go to your physics teacher tomorrow and say, why does Newton's third law mean that a jet engine delivers thrust? And if it's first thing in the morning, he'll hate you. And of course, we can do fantastic things with jet engines. This is what the MOD can do with jet engines when they strap them to fighter jets. So it's pretty impressive. But 9 tons of thrust from a Eurofighter Typhoon engine isn't enough for us. We've run the simulations and we think that the Eurofighter engine on its own can probably get us to about 700, 750 miles an hour. So to get to 1,000 miles an hour, we need something else, and I'm going to demonstrate how this something else works. And fingers crossed, I'm not going to kill myself. Now, we've also developed what will be, when it's finished, the UK's largest ever hybrid rocket. Now, rockets tend to fit into 2 families, solid fuel rockets and then liquid fuel rockets. Okay? And what we've got is a combination of the 2 in our Bloodhound rocket. What I'm going to demonstrate for you, I hope, this evening, is the chemistry of the liquid component of this rocket. So we use a fuel, or technically we should refer to this as an oxidizer. We use an oxidizer called hydrogen peroxide. Now, I'm looking around the audience, and there are definitely some people here this evening who use hydrogen peroxide. What do we use hydrogen peroxide for? Primarily ladies. We use it for bleaching our hair, don't we? Now, does anybody know the chemical symbol of hydrogen peroxide? H2O2, I heard somebody shout it out. So the molecules of hydrogen peroxide are a little bit like water, but they've got an extra oxygen atom attached to them, which means they're not very stable. Do you know what I'm going to do? I'm just going to do it without gloves. Okay, you shouldn't do it without gloves. Now, in here I've got a little bit of 30% concentrate hydrogen peroxide. The hydrogen peroxide we're going to be pumping into the Bloodhound rocket is actually 99% concentrate hydrogen peroxide. And we're going to be pumping 1 ton of this stuff into that rocket engine in the space of 17 seconds. In order to do that, we're driving a fuel pump using an 800 horsepower Cosworth engine. Okay? So we've got a Formula 1 engine that we're using just as our fuel pump in this car. So that gives you an idea of the scale. Okay? Now, hydrogen peroxide is H2O2, and it's not very stable. If it's not very stable, what chemicals is it going to want to break down into? Water and H2O and oxygen. Okay, so the 2 chemicals that it's going to want to break down into are water and oxygen. And when it does this, it releases a lot of heat. Okay, so now we're using a ton of this stuff in the car. I'm going to use about 50 mil of this stuff. I haven't done this for a while, so I hope it's cool. Now, if we're going to turn this into water and oxygen, what are you likely to see at the bottom of the test tube? Bubbles, okay? But to make it more exciting, what I'm going to do is add fairy liquid, because if you have bubbles and fairy liquid, you get fun. So I'm going to add a little bit of fairy liquid. Now this, if we left that there, probably, if we came back tomorrow morning, it would have all decomposed eventually, okay? But we can speed up this reaction, trigger this reaction, by adding what's known as a catalyst. Now if you do GCSE chemistry, you'll know all about catalysts. Catalysts are chemicals that initiate or speed up reactions. And one catalyst that works very well with hydrogen peroxide is sodium iodide. So I've got some sodium iodide solution here, which I'm going to add to this mixture of fairy liquid and hydrogen peroxide. Now the catalyst we've got in the Bloodhound rocket is actually a silver catalyst, a silver-plated nickel gauze, which is at the front end of the rocket there. So fingers crossed, when I add this, something exciting is going to happen. If it doesn't, I'll blame my students who said so. There it goes. That's pretty exciting. And what can you see coming off the top of it? Foam. And if you look at the front there, you can see it. Yeah, there was steam coming off the front of it, which means things were getting very hot. If things were getting very hot, the pressure, I'm going to get hot in this actually, that means that the pressure inside the rocket will get very high. So we're going to pump hydrogen peroxide in at this end. It passes the catalyst. That reaction there starts happening. The pressures and the temperatures inside here become phenomenal. At that point, this solid fuel starts burning. Now this solid fuel is called hydroxyl-terminated polybutadiene. I just memorised that, I have a clue what it is. It's basically, I've seen it, it looks like rubber, and I think it basically is rubber. And so you've got this, now you've got burning rubber, decomposed hydrogen peroxide, that expands out of a nozzle at the back end, again, very high temperature, very high pressure, very high velocity, generating thrust. Now, some of you might have seen recently that we tested the full rocket system for the first time down in Cornwall towards the end of last year. So we know this whole system works now. But this is a movie of a rocket firing we did for a 50% scale version of the Bloodhound rocket out in the Mojave Desert in America the year before last. So you imagine your Andy Green strapped to the front of a rocket twice that size and a Eurofighter jet engine, and your bum is about a foot off the ground. So all of this has led to this question: how do you go about evolving the design of a car like this? Now, back in 2007, this picture landed on my desk with a little note on it from my PhD supervisor at the time, saying, "Please come up to see me. We need to have a chat." And I thought, yeah, we definitely need to have a chat. That was really quite interesting. And what we've done is gone through a series of design iterations between 2007 and 2008. We had to answer this fundamental question before we were willing to release the project to the general public, which is, in theory, is this possible? The first question, when I met with Ron Ayres and Richard Noble in Ron's living room back in 2007, was, you've got a year to go away and come back to us and say, do you think we can do this? If you say yes, we'll launch the project to the public, we'll get sponsors on board and we'll go for it. If you say no, we'll just quash the whole thing and we'll forget it ever happened. Now, as a first job out of university, that's quite a lot of pressure, which is why I was glad we had people like Professor Hassan alongside me to kind of guide me through that process. At the end of 2008, we were confident that in principle this could be done. We didn't have a design that could achieve it, but we were fairly confident that you could do it in principle. And then it's taken 4 years to evolve the design to this car that you see in front of you today, which we're actually building. And this is the journey we've gone on. Now, each of these individual cars, now, what hopefully you can spot is that in the early stages of the design changes, the design changes we were making to the car were really quite big, they were quite fundamental changes, things like where the engines are going to go, how many intake ducts we're going to have, where the wheels are going to be positioned. And then as we get further and further through the design iteration, it becomes quite difficult to tell what we've changed in the car towards the end. It's very difficult to see with your naked eye what we've done. We go from config 11 to config 12, which is the car we're actually building. And to give you an idea how much work goes into this, for every single one of these iterations that we go through, to go from here's a new design, to running all the computer simulations, to analysing the data we get from the computer simulations, to sitting down with the rest of the designers and deciding what changes we're going to make, probably took us, on average, somewhere between 3 and 4 months. So that represents, to me, an awful lot of work. So this is what the car looks like that we're now building. And for me, as someone who's very much a theoretician, this is a very exciting time because we're now turning something which has just been theory for me. The car has been pictures on my computer screen, numbers in a computer, into something real. Once we finalise that outer shape, we were able to start defining the internal structure of the car. And we're now actually manufacturing it. I was proudly the very first person to sit in the cockpit. I just happened to be by the doors of the Bloodhound Centre in Bristol when the carbon fibre front end of the car arrived, and I quickly jumped in and had my picture taken, and the next day that's on the BBC website, that picture. So these are really exciting times, but not as exciting as it's going to be when we actually run this thing. We're hoping that we can get the car built by the end of this year, start doing what we're calling our low-speed testing. Now for us, low-speed testing is up to about 300 miles an hour on a runway in the UK later this year or early next year. And next summer, our summer, the South African winter, we will head out to South Africa and start testing the car. So just to kind of wrap up, what I want to do is just talk you through what I always refer to this as a typical 1,000 mile per hour run of the supersonic car. There will be no such thing as a typical 1,000 mile per hour run. We'll do it once, or we'll do it twice in 2 directions, and then we'll stop and we'll have a big party. So what I'm plotting here is on the red line, speeds, this is the speed of the car, and on the blue line, the acceleration of the car. By the way, if you're a teacher and you teach physics or maths, you need to use this kind of stuff, because I remember, I went to Technocamps, which is a fantastic school, really, really good school, but I remember doing like velocity time graphs and speed time graphs, and the teacher would give you kind of applications like, here's your mother's shopping trip to Tesco's in a speed time graph, you know, analyse when she stopped at the traffic lights. You know, that's how you turn kids off maths. Talking to them about supersonic fighters and Bloodhound supersonic cars, that's how you get them engaged in maths. So what we've got here is a blue line, which is the acceleration, and it's measured on the right-hand side here on this axis, in G, so multiples of 9.81 meters per second squared. So when it's above 0, it's accelerating. When it's below 0, it's decelerating. And on the red line here is the speed of the car in miles per hour. Now, those of you who know about how acceleration and velocity time graphs are related, what you should be able to spot is that the gradient, or the slope of this line, is directly related to where this acceleration line sits. Okay, so see if you can spot that. So initially, we'll accelerate off relatively gently, simply because we're running on a desert surface, there'll be a lot of dust, and what we don't want to do is suck up lots of that dust into the intake duct and ruin the engine. But once we get up above 100 or so miles per hour, Andy can like what we call the reheat, or the Americans call the afterburners on the jet engine. So at this point now, we've increased the thrust, so you can see the acceleration line shoots up because the thrust has shot up. We've got 9 tons of thrust sitting behind Andy. This will take us to just over 300 miles per hour, and then at this point Andy will light he will turn the throttle on the Cosworth engine to pump the hydrogen peroxide into the rocket. And the rocket initially starts up in monopropellant mode, so it's just the hydrogen peroxide breaking down into water and oxygen, generating the thrust. Eventually the rubber inside the rocket starts burning, and the rocket engine is now generating 12 tons of thrust. So Andy is now sitting on 21 tons of thrust, which is a lot. At this point he's accelerating at about 2.5 G. That means his speed is increasing at about 60 miles per hour per second. Okay, just have a think about that. To give you an idea of how that would feel in terms of G-force, imagine travelling at 60 miles per hour in your car, slamming on the brakes and coming to a stop in the space of 1 second. That's the force he's experiencing constantly on his body at this point. We then enter the measured mile, which will be in the middle of the track. At 1,000 miles per hour, we cover that measured mile in 3.6 seconds. Again, that's pretty fast. And then we've got the equally difficult job of getting this 7 tons of metal and carbon fibre and Andy Green to slow down. So we've got a series of air brakes and parachutes that will be activated to make sure that this acceleration line stays low enough so that the gradient of the speed line is steep enough to get him back to 0 before he hits the mountain at the end of the desert in South Africa. Because at the end of the 10-mile track we've got, there's a big mountain. Then, we've got to turn the car around, get it refueled, the rocket recharged, do the whole thing in the opposite direction within the space of an hour to claim the Guinness World Land Speed Record. So in the language of mathematics, that's what it looked like. I've got a couple of movies that have been made of what this looks like, just to finish now. A couple of years ago, Richard went to the MOD and he said to them, when we're ready to go with Bloodhound, we're out in the desert in South Africa, would you be interested in racing us, you and the Eurofighter Typhoon, against us in Bloodhound? They came back to us and they said, we'll have a think about it, and they're still thinking about it, because they know who would win that race. I don't think it's ever going to happen, but if it did happen, it would look something like this. Still not sure how the score came up to the end of the track before the car did. So that's a bit of fun, I guess. And to give you an idea of what would be going on inside the car while all of that is going on, here's the most recent movie that we've made. So you can actually see all the internal systems in the car in operation. This is the hydrogen peroxide fuel tank here, taking a ton of hydrogen peroxide. This is the Cosworth engine connected to a fuel pump. Rocket engine and the catalyst pack at the front. That's the bit that triggers the hydrogen peroxide breakdown. The rubber solid fuel inside the rocket and the nozzle at the back of the rocket. Thank you very much for coming tonight. If you are on Twitter and you want to find out more about the project, you can follow Swansea's involvement by following me, Ben Evans, or the project in general at this address here. And as I said earlier, if you're connected to a school and you'd like your school to get involved, come and speak to me at the end, or visit the College of Engineering website at Swansea, and there's information there about how you can get more involved. Thank you very much. Okay, I've been asked to present this to a representative from Leith Albert College, whose name I've already forgotten, and I'm really sorry. Sunny Bambara, I hope is going to come. And the students. And this is the winning card. It was the winning card. If I haven't run too late, you can take questions now. Oh, right, okay. Go on, Liz.
Is that exact model?
Yeah.
Oh, that's cool.
So I think I've been asked to kind of referee questions. But would you like to come up and help with some questions as well, please? There's a gentleman standing at the back where we'll go first, then there's a young lad in grey where we'll go second.
Finally, American gamers, was big happy when he was involved with the arts of the other group, the SEs and they have.
Right. Yeah, the competition. Yeah, the Americans do want it back. To our knowledge, there are at least 2 cars that in principle could be competition from America. One is the Spirit of American car that was being developed by Steve Fawcett until he sadly threw himself into the side of the mountain. And it's now been bought by someone else. We don't know who that someone else is at the moment. There's also the North American Eagle car that you might have seen. These are a lovely bunch of guys who we're in contact with. They're basically a bunch of retired engineers with too much money and spare time on their hands. We're a little bit concerned about them because we're concerned that they're going to kill somebody, which will not put the land speed record in a good light. So we're encouraging them to stop where they're at. To be fair to them, they've managed to get the North American Eagle up to about 450 miles an hour, but we're encouraging them not to go any further than that. The 2 cars that we think could be genuine competition and who we hope will be genuine competition are the Australians. They've got a car called the Aussie Invader, a guy called Roscoe McGlashan. They're at a similar point in the development of their car to us, and they've set themselves a target of 1,000 miles per hour also. But there's also, we've recently discovered, a New Zealand team as well, who seem to have a reasonably good design that they're developing. And I forget the name of that car. But we think that the genuine competition, and we hope it will be genuine competition, will be from the Australians and the New Zealanders. We'll get there first.
And then there's the young gentleman in grey, please.
Yeah, good question. I think if we knew of somewhere that had a long enough, flat enough, straight enough piece of tarmac for us to run on, we'd seriously consider it. The problem we would have with running on tarmac is the wheels that we can't have tyres on them because the tyres will just blow themselves apart at these speeds. So actually it's good to have a little bit of compliance in the surface itself because we've got solid metal wheels, and solid metal wheels probably wouldn't do very well on tarmac, but it's something we probably would consider if it was available to us. Now when we think of a desert, in our heads you might think, oh, lots of sand. In reality, the desert that we're running on, the Haxkin Pan in South Africa, is more like a dried out mud surface. It's actually a very hard surface, but when the wheels interact with it, they will engage with it and dig down into the surface. So we actually think that the surface we've got is probably the best we could run on. Where are the engines? Okay, good question. So we've got the jet engine, which is in the top of the car here, so it sits. So you can see the jet exhaust is at the top at this point, and it comes down to about this point in the car. Then we've got the rocket engine, which is at the bottom, so you can see the exhaust of the rocket engine there. It's a lot thinner than the jet engine, and longer, so that runs to about here on the car. And then we've also got the Cosworth engine, which is just driving the fuel pump, and that sits just behind the driver's cockpit.
Gentleman in black in the front row, and up comes the chap in the stripy top on the side there.
Why was the acceleration curve to shoulders not more constant, smoother?
Yes. Why was it not smoother? I guess because we're engaging different parts of the thrust at different times. So the only bit of thrust that we've got good control over is the first part of the jet engine, because you can actually throttle that back and forward. The afterburners, once you turn them on, that's kind of like a step change in the thrust. And the rocket, the problem with rockets, and the problem we think the Australians are going to have, because they've got a pure rocket car, is you've got very limited controllability for the rocket. As we experienced outside earlier, a rocket essentially is either on or off. You light it, and you've got maximum thrust. You turn it off, and you've got no thrust. So when you engage the afterburners, there's a step change in the thrust, and then when you kick the rocket in, there's a quite rapid change in the thrust. So it's very, very difficult to control that smoothly. The reason we've got the jet engine is that gives us a level of controllability over our thrust. And certainly for the testing phase of the car, where we're trying to understand how the car behaves at the lower speeds, that gives us a lot more flexibility to say to Andy, right, on your next run, we want you to go to 210 miles per hour. You can control that on the jet engine, which would be very difficult to do with just a rocket.
Okay. Gentleman on the side there.
Yeah, Ben, just wondering, is there any risk of driver or pilot disorientation at that sort of high speed? And is there any sort of lateral monitoring of G-force that can come in and control or maintain a safe situation?
Yeah, good question. We've had lots of questions in design meetings about any kind of overrides we're going to have, where we would monitor Andy's response and in principle could override him. He's a fighter pilot, so he always says, no way. I'm not. He trusts himself implicitly, and he says the safest thing is that we don't have overrides like that. We will be monitoring him, and if he were to pass out, we will be able to shut the car down, release the air brakes, parachutes, stop the car. In terms of its actual kind of directional control, that's entirely controlled by Andy. And actually, although we talk about 2.5, 3G, compared to what he experiences in a fighter jet, that's next to nothing. He won't even be wearing a G-suit in Bloodhound. He's competent, he can handle that without a G-suit.
Yeah, sorry to carry on. He hasn't got much information. There's a very plain colour.
Yeah.
Whether he can.
Yeah. So what he does, and you might have spotted it on some of the movies that are based on that. We'll put literally this is how we do it. We paint a white line on the desert surface. So we say to Andy, your job is to stay on that white line. And then some of the footage, if you YouTube it when you go home, you can see that actually in thrust he veered quite significantly off that white line, and you can see straight away when he's veering off it, and his hand goes back to correct. So that's what he's using to orientate himself.
Thank you.
Okay, another couple of questions. Let's take on the young lady here in the green top, and then there's a gent at the front in a black shirt. And we'll keep doing that until we've done everybody.
On the same point, really. How sort of directionally stable is it?
Yeah.
Because there's a lot of stuff at the back, it's very long thing.
Yes, good question. How directionally stable it is a question I'm currently asking. So, so we've done all our kind of on-design. So we've kind of designed the car, assuming it's always going straight ahead. And now we're asking the question. The final questions we're asking are, how big do these winglets need to be? How big does that fin at the back need to be? So at the moment we're doing a series